In this particular chapter, we're going to go ahead and take some time to study polynomials and polynomial functions. And before we get all into this, I need to remind you we've done some of this before. The first type of polynomial we spent time studying was your favorite and mine, y equals mx plus b. This was our linear polynomial, and why it was a polynomial is because this x here was raised to the first power. So we could have called this guy a degree 1 polynomial. And this is purely for your visual entertainment. You don't need to write anything down yet. The next type of polynomial we spent time studying was y equals ax squared plus bx plus c. This is commonly referred to as a quadratic polynomial or a degree 2 polynomial. So a lot of what we start off with in this chapter relates to some things that we've already done. So we did a linear polynomial, y equals mx plus b, so there's your line. And we did a quadratic polynomial, one that would make a parabola. Before we get all into the different types of polynomials and what is a polynomial, we have to, of course, talk about some basics. And the goal of today's lesson is to explore our properties of exponents. These properties are going to allow us to simplify our polynomials before we actually get into graphing them or solving them. So we have just a little bit of background knowledge to go ahead and get started with. And you might notice this chart is the first chart in your Chapter 5 note packet. I put it right front in the middle, or right front and center there, just so that you have it to refer back to as you're working through your problems in this chapter. So it's going to be the first thing that we start off with, and you'll take some time to refer back to it, every so often as we go through the chapter. What I also have to tell you about this chart is that it's just a bunch of shortcuts. So if you're ever in doubt about what to do, you could, until you kind of get the hang of it, definitely take the long way. And I'll show you what I mean by shortcuts in just a few moments. So before we get started, let's talk about something that doesn't necessarily pertain to multiplying or dividing monomials or polynomials, but we want to talk about what it's like to add or subtract some monomial terms. And in that case, you might remember the phrase that whenever we see that big plus or minus sign in between, we actually work to combine like terms. We don't change the common variables or the exponents involved. Remember, like terms is a definition back from chapter 1. Like terms are just terms that share the exact same variable part. So you could jot that down real quick in your notes. The exact same variable part. That is the definition of like terms. So for instance, when I look at this first example here off to the right, see how we have 9x squared y minus 10x squared y. They have the exact same variable part. X squared y is in both of those terms. And again, terms are just things sort of separated by a plus or a minus sign. So here, if I have negative 9x squared y minus 10x squared y, that just makes negative 1x squared y. So you just put the 9 minus 10 together, and then the x squared y just comes along for the ride. So if we wanted to subtract 6w from 8w, we would be doing 8w minus 6w. Do you see how we have the exact same variable part? Both of those terms have a w attached to them. So I can just combine the coefficients. 8 minus 6 is 2, and then the w comes along for the ride. Now what we're going to go ahead and talk about is, what happens if we multiply or divide monomial pieces. And, back in the day, I'm going to go ahead and add a slide. This was a shortcut. What we're about to take care of is something as simple as like x squared times x to the third. And before we had these cool little shortcuts, you might even think about this problem as, x squared. We know that that's just x times x. And x to the third is just x times x times x. And then you see this dot here? That can come down too. So what am I actually multiplying together? Well, I see I have x times x times x times x times x, or x to the 5th. And, you could do this with like x to the 10th times x to the 20th, however you want to work it. But in actuality, when we're multiplying these things together, all we need to do is just add the exponents. So why would you write this all out when you can just observe a pattern of adding the exponents together? And that's what this first property is kind of getting at. If you have x raised to the power of a times x raised to the power of b, well, that's just the same thing as x raised to the a plus b power. So we're allowed to add the exponents when you have a product of like bases. So for instance, over here in number 1, if I have h squared times h to the 6th, well, we could write that as h times 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 h, and we'd have 8 h's staring at us, but who wants to write all that, right? So we're going to just go ahead and use our product property and find the sum of 2 and 6. H raised to the 2 plus 6 power is the same thing as h to the 8th. And right now, you're probably saying, Mrs. Lucas, do I have to show the work for 2 plus 6? Again, the goal is to write one step worth of work and then your final answer. So you're going to see that some of these problems have 2, 3, 4 steps. Really, I don't need an essay. I just need to know that something went on in your brain to get the final answer. So you'll copy the problem, show one step worth of work, and then go ahead and give me a final answer. In number 2, when I look at that, I'm like, whew, I see some like bases. I see some A's, I see some B's, but it's all kind of scrambled up right now. So I'm going to go ahead and use my associative property of multiplication and just kind of rearrange some things. So for instance, I can multiply the -2 times the 7, and I can multiply my A's together, and I can multiply my B's together. I'm allowed to break apart multiplication. Oops, there's no 2 there. I'm allowed to break apart multiplication, really however I want. You can put dots in there if you'd like. So now I would just go ahead and evaluate each piece. So for instance, when I look at the product of -2 and 7, I know that that's just -14. And then when I look at the product of a squared times a to the 3rd, I know that I'm allowed to add those exponents together. So the sum of 2 and 3 is just 5. And then b times b is just b squared. So that is my final answer. Again, at least one step worth of work. That was the couple examples of our product property. The next property we have is called our power rule. And again, we could do this property the long way. If you really wanted to, kind of do it out, if you're a skeptic, what we're about to explore is the idea that if you have x squared cubed, we're actually allowed to multiply the exponents together. So that's x to the 6th. But if you're a doubting Thomas, so to speak, you could just, x squared to the 3rd power is just x squared times x squared times x squared. And if we go off of the logic as we did up above, x squared is just x times x squared is just x times x squared is just x times x, and you could bring down the dots that are in between. So do you see how many x's we have? 1, 2, 3, 4, 5, 6. Now, who wants to write all of that, especially when there's, multiple parts to each of these problems? Not me. So what you need to understand is that we're just allowed to multiply that number that's outside the parentheses under a couple of cases. We're allowed to apply the power rule, to be honest. I'm going to add a note here. You're allowed to apply that power rule as long as there's no plus or minus in the parentheses. As long as there's no plus or minus in those parentheses, you're free to distribute this b to that a right there. So what I'm saying is you're allowed to raise x to the power of a times b. So for instance, here in number 1, I'm allowed to raise x to the power of 2 times 3. So that's x to the 6th. The other thing you need to remember is that numbers have exponents. So this -2 right here, it's raised to a power. It's raised to the first power. So my most common mistake that I'll see is students forgetting to distribute that 2 right there to the 1 that -2 is raised to. So remember that your integer values in the problem are going to have exponents. -2 is raised to the first power. That's just something to keep in mind there. But again, I see no plus or minus sign in that quantity, so I am allowed to distribute that 2 in. So I'm going to take -2, and I know that 1 times 2 is 2. So that's -2 squared. And then I'm going to go ahead and fix up this m. I know that m to the 5th squared is the same as m to the 5 times 2. The product of 5 and 2 is 10. And then I have this m to the 3rd out here. I'm going to bring him down for the ride. And then I'm just going to simplify each piece. So if I do -2 squared, remember that's -2 times -2, which is a positive 4. And then do you see how you have m to the 10th and m to the 3rd? We're allowed to add those exponents together. So that's going to be m to the 10 plus 3. So this will be 4m to the 13th power. And that's your answer there. I always circle my final answers to distinguish them from the work. So we are allowed to distribute an exponent outside of the parentheses as long as there's no plus or minus. Now, what we have here in the next property is called our quotient rule for exponents. So let's take a second to talk about how that is also a shortcut. So let's say, for instance, you have x to the 3rd over x squared. Well, if we write that out, x to the 3rd is just x times x times x, right? And then x squared is just x times x. Well, if we use our reducing rules from middle school, we know that if you have x over x, that's just 1. And over here, I see another pair that would reduce. X over x is also just 1. So what I have left over is just one little x to the first power on the top. So I have 1 times 1 times x to the first. Well, 1 times 1 is 1 times x to the first is just x to the first. So what did I actually do here? I subtracted. 3 minus 2 gives me 1. So that's the shortcut we have for a quotient of like bases. So officially, this gives us a shortcut. If I have like bases in a quotient or in a fraction with one another, I am allowed to subtract the exponents. So there'd be x to the a minus b power. So if I look at problem number 1 here, remember this x, it has an exponent, it's raised to the first power. I would reduce the 27 and the 42 like I normally would. I know that 27 and 42 share a common factor. Both of those things are divisible by at least 3. So I would reduce out the factor of 3. So 27, 3 goes into 27 9 times, and then 3 goes into 42 14 times. So I reduce the fractions like I normally would. And then 9/14, that doesn't reduce anymore. 9 and 14 don't have any common factors. Now we take a look at x to the 5th over x to the 1st. And we're allowed to subtract those two exponents. So I do x to the 5 minus 1. So what I get is 9 over 14. And then 5 minus 1 is 4. Notice I always do my subtraction problem on the top. That becomes important in a couple of minutes. Okay, number 2, again, I see parentheses in the problem, so I kind of follow the order of operations just a bit. So I'm going to go ahead and work with those parentheses first. And I am learning in, the above property, our power rule, that I can multiply 2 times 2 to get 4. And then y to the 4th is on the bottom. 4 minus 4 gives me y to the 0th power, which is actually 1. And we're going to talk about that in just a few minutes. But if you think back, y to the 4th and over y to the 4th would be 1. Okay. Next up, we have our negative exponent rule, and I have a special name for this guy. I call it the upstairs, downstairs rule. And it kind of works like this. If you have a negative exponent in the numerator, to make it positive, you move it to the bottom or downstairs. And if you have a negative exponent in the downstairs, to get rid of the negative exponent, you move it upstairs. So there's 2 pieces to this rule. There's the upstairs and the downstairs. Make no mistakes about it, though. Negative exponents are bad guys. You're really never allowed to leave them in an answer that has variable expressions. So negative exponents are going to be something that we always work to get rid of. So if you look at x to the negative a, what we can see here is, you have that bad guy in the problem. So we have to talk about how to get rid of that. And again, it's a shortcut from back in the day. I'm going to actually just work with straight numbers here. You might, for fun, in your calculator, enter in 2 to the negative first. So let's say you entered that in your calculator. Your calculator is going to spit back out at you 0.5, which is 1 over 2. See what they did there? See what happened? To get rid of this negative exponent, this 2 moved to the bottom of a fraction. So it got demoted and went downstairs. Now, conversely, if you went ahead in your calculator and you typed in 1 divided by 2 to the negative first, your calculator would give you 2. Don't forget, you always got to put your, bottom in parentheses there. But it would give you 2. Do you see what happened there? It was a negative exponent in the bottom. And to make it 2 to the positive first, it had to move upstairs. So if you have a negative exponent in the numerator, it moves to the bottom. A negative exponent in the bottom gets promoted to the top. So let's go ahead and make this official. If we have x raised to the power of negative a, that's going to be the same thing as moving that x to the a to the bottom. And then you can't have, a topless fraction. So we need a placeholder. We put a 1 up there instead. So let's take a look at a couple. Number 1. First of all, this negative 5, again, it has an exponent. It is raised to the first power. My friends, 1 is a positive number. This is not a bad guy. Negative 5 to the first power is perfectly fine. It doesn't have a negative exponent. It gets to stay put. It does not have to move. Negative 5 to the first power can stay where it is. It's, in the top to begin with, so it can stay put. The bad guy in this problem, I'll put him in red. The bad guy in this problem is x to the negative second. So if I want to get rid of that exponent of negative 2, I have to move it to the bottom. So the final answer to this is just negative 5 over x squared. Let's take a look at number 2. You have 4/8. That still reduces to be 1/2. I'm not changing that on you. But what I notice is that I have like bases. I have 2 k's there, and I'm allowed to subtract my exponents. So I have k to the 2 minus 5. So I still have 1/2 and then k to the negative third on top. Remember, my numbers have exponents. This is 1 to the first, and this is 2 to the first. And because 1 is positive, the 1 and the 2 can stay where they're at. They are just perfectly fine. The bad guy in the problem is this k to the negative third. That factor has a negative exponent, and we're not allowed to leave negative exponents in our final answer. So since this negative exponent is in the numerator, to make it positive, I move it to the denominator. So you see that you have 1 over 2k to the third. If you're really struggling with like, I just don't know where to put the final answer, I do have a little sort of analogy for you. It's like a football analogy. Do you see this k squared over this k to the fifth? I feel like this fraction line acts like a line of scrimmage. So you have, 5 k's on the bottom stacked up against 2 k's on the top, right? So I'll give you a little visual. So I have 2 k's on the top stacked up against 5 k's on the bottom. Well, this guy takes out this guy takes out this guy, and then I have 3 k's left on the bottom. See how I have 3 k's left on the bottom in my answer? So you can always think of it for now as these k's sort of doing battle over this line of scrimmage like in a football game. So you'd have 3 men, if you're an X's and O's type of person, you'd have 3 k's on the bottom or 3 k's below that line of scrimmage. So that helps a lot of my students too. I hope that helps you. Okie dokie. And the last rule we have is our zero exponent rule. Congratulations, you're going to make it. This property is super easy. Anything raised to the 0th power is 1. Careful though. Remember, this 7 has an exponent. 7 is raised to the first power. X to the 0th power, however, turns into 1. So this is actually 7 times 1, which is 7. So just keep an eye out. Remember, your numbers have exponents. And then if you look, at our power rule up top, we're allowed to multiply that 4 times 2 to get w to the 8th. And then this w to the 8th just comes along for the ride. And you see how we have same thing on top of same thing? A quotient of like factors there is always going to divide out to be 1, right? Well, now mathematically speaking, we're seeing why the 0 exponent power gives us 1. Well, we're doing 8 minus 8, which is to the 0th power. And we said, well, hey, this has to be 1. They reduce out. So w to the 0th power also has to be 1. So you're kind of seeing why that property is a shortcut, actually. So anything raised to the power of 0 can be 1. So this chart is here for you to reference throughout the course of our time together. Right now, we're going to go ahead and turn the page and take a look at some independent practice. It's now at this point in time, I'm going to go ahead and have you take just a second to go ahead and pause your video and go ahead and give these a try. And then we'll be back to show you some answers in just a few seconds. And many of you know, we already kind of worked some of them out. Let me bring the screen shade back in here a little bit. Not ruin all the surprises at once. So this is just a little bit of practice. Hopefully it went okay for you. It's now at this point in time, I'm going to go ahead and go over them. So let's see how you did. Okay, first things first. Oops. Need to bring this down a little bit. Remember at least one step worth of work. You get to pick the step, however you want to work it. But I need one step worth of work. So for part A, I did use my power rule. I found the product of 2 and 3, that is 6. So 6 to the 6th power. Threw that in my calculator. 46,656 is your answer. For the next one, I used my quotient power. I am allowed to subtract my exponents here because I have a like base of 4. 5 minus 3 is 2, so 4 squared does give me 16. Next, we had our negative exponent rule. My upstairs, downstairs rule says That 7 to the negative fourth is a bad guy, so I have to move it to the basement. Think of it like a prisoner, you know? You gotta move it downstairs, keep it out of sight. So you got 1 over 7 to the fourth power, and you see there that I forgot my 1, didn't I? Oh man, look at that. Gotta fix it up. So what we have is 1 over 2,401. Okie dokes. So now we start to throw letters into the mix a little bit. Let's talk about that. The first thing I do is I simplify anything in the parentheses, kind of going back to my order of operations. So I did have to distribute this 3 into the parentheses. Remember, we are allowed to do that as long as there's no plus or minus in the parentheses. If there's a plus or a minus, you're foiling or distributing, and which is totally different. So I can't use my power rule if there's a plus or a minus, but hey, I didn't see a plus or a minus in here, so I'm going to distribute away. 3 times 5 is 15. 3 times 2 gives me 6. And then I did use my quotient rule. 15 minus 15 does give me x to the 0th power. 6 minus 8 gives me negative 2. Remember, anything raised to the power of 0 is 1. Y to the negative second has to move to the bottom. So we have 1 over y squared as our answer there. For part B, I did distribute that 2 into the parentheses. I'm allowed to use that power rule as long as there's no plus or minus in those parentheses. So I have a to the negative 8 over b to the 4th. And then a to the negative 8 is a bad guy, so it has to move to the bottom. So we end up with 1 over a to the 8th, b to the 4th. And then a couple more for you. Number 1 here. What we're going to go ahead and do is distribute the negative 1 in. We have a to the negative 5th over 8. I'm sorry, I think I said a. 8 to the negative 5th over 8 to the negative 2 is one way to do the problem. Another way to do the problem is just to work out the problem in the parentheses first, which is also what I did. I just did 5 minus 2, and that's 3. Distribute your negative 1 in there, and you get 8 to the negative 3rd, which is 1 over 8 to the 3rd, which is 1 over 512. For number 2, again, I simplified what was in the parentheses first. I see I have a bad guy hanging out in there. So I moved it to the bottom of the fraction. I have x squared over y to the 6th. Distribute your 7 in. 7 times 2 gives me 14. 7 times 6 gives me 42. So the answer for number 2 there is x to the 14th over y to the 42nd. I believe that takes care of that page. We have one more on the next page, though. Taking a look at number 3 up there. And then we'll work out a little bit of scientific notation together. What we have, when I started number 3, is I just crossed off the b's. I tried to simplify what was in those parentheses first. So these b's reduce off. And then I did go ahead and I did 2 minus 5. 2 minus 5 is negative 3. And then I did use my power rule, so I took negative 2, raised it to the 3rd power. And then the product of negative 3 and 3 is negative 9. So I have negative 8 over a to the 9th power. These rules can actually be applied to scientific notation, too. That's what we're going to go ahead and take care of right now. And just to review, a number in scientific notation, it's just a way of writing a very large or small number as a product of a number between 1 and 10, not including 10, and 10 raised to a power. So this is a super easy way to work with really big and really small numbers. And we have a little word problem. It's kind of gross. Look at that. Ugh, all those locusts. So disgusting. We'll read it together. We have a swarm of locusts. A swarm of locusts may contain as many as 85 million locusts per square kilometer and cover an area of 1,200 square kilometers. About how many locusts are in such a swarm? Well, if I want to find the total number of locusts in this giant swarm, basically I'm going to have to multiply two values together. I'm going to have to multiply the number of square kilometers we actually have times the number of locusts in each of those square kilometers. That's how I would get the total number of locusts in this case. So now I'm going to start to fill in what I know about the problem. For instance, the problem lets me know that this particular swarm of locusts takes up 1,200 square kilometers. They also tell me that in each of those square kilometers, we have 85 million locusts. That's 85 with 6 zeros on it. And I personally don't really want to work with all these zeros, so what I'm going to go ahead and do is rewrite each of these numbers in scientific notation. Just to review, if we wanted to take 1,200 and write it in scientific notation, your decimal point's normally hanging out here to the right. We need to move that decimal point until we get a number that is between 1 and 10. So if I just move it one time, I'm at 120. 2 times gets me to 12, so closer. 3 times is the magic number because 1.2 is a number between 1 and 10. And because 1,200 is a big number, I have to raise 10 to a big power. I swooped that decimal over 3 times. Let's try it again with 85 million. So the decimal point's normally chilling all the way off to the right. And I need to swoop it 1, 2, 3. So I'm at 85,000 right now. 4, 5, 6 gets me to 85. 7 gets me to a number between 1 and 10 because 8.5 is a number between 1 and 10. And I did swoop that decimal 7 times. The beauty here is that I can use, this is just all multiplication. If I wanted to put dots in where these x's are, I could definitely do that, right? And because multiplication is both commutative and associative, I can group the 1.2 together and the 8.5 together. And then I can multiply the 10 to the third times the 10 to the seventh together. So see how I can use my properties of exponents now? 1.2 times 8.5, you could grab your calculator for that part. I know I'm going to. That gets me 10.2 times, and then I could just add 3 plus 7 because that's a product of like bases. 3 and 7 is 10. Now I know what you're thinking. You're like, Mrs. Lucas, that violates the definition for scientific notation because 10.2 is not a number between 1 and 10, and you would be correct. So you could take one more step, and I'm going to show you what's going on in my head right now. 10.2 is like 1.02 times 10 to the first. So I just rewrote this in scientific notation. Bring down my 10 to the 10th from the previous portion of the problem, and again I can add my exponents together. So this is actually best written as 1.02 times 10 to the 11th power. And that is locusts, friends. Ew, so many bugs. So disgusting. So 1.02 times 10 to the 11th locusts are in this particular swarm.